In this video, we're going to talk about the Bronsted-Lowry theory. It was proposed by Johannes Nicholas Bronsted and Thomas Martin Lowry. So what it says is an acid is a substance that donates a proton, or an acid is a proton donor. So let's take an example. Say we have some hydrochloric acid and water. So that gives us the chloride anion and the hydronium ion, or the H3O+. Here, the hydrochloric acid donates a proton to water. See, it does not donate a hydrogen atom, it donates a proton. The negative charge, or the electron, remains here. And this water gains a proton and forms hydronium, H3O+. See, let's see what a base. A base is a proton acceptor. It accepts a proton. Let's take an example. Say we have some ammonia and water. So that gives us ammonium, or NH4 plus, and OH minus. So this ammonia is a base and it accepts a proton from water to form NH4 plus. And since a proton is given out by the water, the OH remains and the electron, so it forms OH minus. You can notice the water here is acting as a base and here it is acting as an acid. These are called amphoteric substances. Amphoteric. That is, those that act both as an acid and also as a base. You can see that hydrochloric acid is more acidic than water, and so it is donating a proton. But here the ammonia is more basic than water, and so it is accepting a proton from water and forming NH4 plus. So water is an amphoteric substance. It acts both as an acid or a base, but if you see its pH, it's neutral. Now let's talk about neutralization. So neutralization, according to the Bronsted-Lowry theory, is the transfer of proton from acid to base. So let's take an example here. We have hydrochloric acid and ammonia. So that gives us the chloride anion and the NH4 plus. So you can see here hydrochloric acid donates a proton to the NH3 and what remains is the chloride anion, and here it forms NH4 plus. So you can see this over here is an acid and this is a base. And if the reaction also went in reverse, then you can see that chloride ion would want to accept a hydrogen. And who accepts a hydrogen? A base. So this acts as a conjugate base. And this accepted a hydrogen, and if the reaction went in reverse, then this would want to give out the hydrogen. And who wants to give out a hydrogen? That is, or a proton, that is the acid. So this acts as a conjugate acid. I meant proton, by mistake I said hydrogen. Conjugate acid. So we'll see what a conjugate acid base pair is here in more detail. Let's take an example for that. It will help us. Suppose we have some hydrogen fluoride. It's a weak acid, so it's in an equilibrium reaction with fluoride ion. So we remove a proton here and we add a proton here. So if we remove this is an acid, this over here is an acid. And when we remove a proton, or the acid donates a proton, it forms its conjugate base pair, which you can say as conjugate base. So when the acid donates a proton, it forms a base, and that base is called a conjugate base. And if this was the base that we took and the reaction went like this, we'd say this is a base and this is the conjugate acid. This is just basically the Bronsted theory's properties, which state that what is an acid and what is a base. This acid donates a proton, a base accepts a proton, and that is a conjugate acid-base pair. If the acid is weak, then the conjugate base will be strong, and if the acid is strong, then the conjugate base will be weak, and vice versa. If the base is strong, the conjugate acid will be weak, and if the base is weak, the conjugate acid will be strong. So because you can see, if a hydrofluoric acid was a strong acid, then the reaction will progress more in this direction and less in this direction. So there would be more concentration of fluoride ions. And then since there is more concentration of fluorine ions and still the reaction is progressing in this direction very less, we can say fluorine is a weak base. But this is not so. Hydrofluoric acid is a weak acid and fluorine is a strong base. We can say a strong base because it's a conjugate base of a weak acid. So if it's confused, I recommend you to watch the conjugate acid base video. And now we're gonna go to the limitations. Just like the Arrhenius theory, this theory also has its limitations. So it cannot explain the acidic nature of non-metal oxides that do not have a hydrogen in them. For examples, same the carbon dioxide and sulfur trioxide. So these non-metal oxides' acidic nature cannot be explained by the Bronsted-Lowry theory. And the other limitation is that it cannot explain the neutralization reaction where the transfer of proton does not take place. For example, we have calcium oxide and sulfur trioxide, and this forms calcium sulfate. But this cannot be explained by the Bronsted-Lowry theory as no proton transfer takes place here. So this is all about the Bronsted-Lowry theory, and to explain these limitations, a later theory was proposed, that was the Lewis theory. We'll talk about that in another video. This is it for this video, so thank you.